Alright, we're going to be covering limits at infinity now. And limits at infinity basically are something we've already dealt with, but previously we would say the limit didn't exist, which is true. There's a definition of what a limit is, and what we are going to be calling limits at infinity don't fit that, but we're just going to kind of loosely call it something else, something that it technically isn't. Okay, so that'll be fun. So first we're going to build our intuition with some pictures, just to show you what a limit at infinity is like. And we'll talk about, limits from the left and from the right for limits at infinity. We're going to be able to find limits of infinity, or limits at infinity, once we understand what causes a limit to go to infinity. And then we're not going to get tricked when we're finding those limits, especially when we don't have a graph to look at. We're going to just have a function, an equation to use. So let's get started. Let's start with an intuition with pictures. And let's just do that right here on the same screen. Okay, so here is a graph, and I'll show you a limit at infinity. Okay. Here's some function. Alright, and the book gives this really crazy looking explanation. And it pretty much amounts to this. Right? First of all, let's look at it. Here's the C value. Right here, C. The limit as x approaches c of this function f, right, this is f of x, well, it doesn't exist really, but we could say it is infinity because look at it, they're both going off together, meeting the same number, quote unquote infinity. This number, it's not really a number, we should know that, but we say it this way. It's a little faster and it's easier to talk about. So the book gives an explanation pretty much like this. I'm going to try and simplify it so that if you were to read it yourself and you were to listen to this explanation, it would make a little more sense. They're saying pick some value of y, some y value on this graph, and call it m. And they're saying, okay, so here's m, right? And what we're saying is, if this is true, if the limit as x approaches c of this function is infinity, what we're stating is that there are some boundaries, some distance away from c, okay? And this distance, from here to here, and also from here to here, is going to be called delta. And this is also delta, okay? And it's just basically, like a force field or a boundary or sidelines or something, however that helps you to see that there's just this area in here that, given that we've picked an m, any value that we pick in here for x, if we pick this x and input it into the function, no matter where we pick an x inside these sidelines, when we put it into the function f, we're going to get out something that's bigger. The output's going to be bigger than m. Okay, that's a really complicated, I would say fancy, well-defined way of saying that both of these sides of this function go and get really big, and they don't come back down. They don't do anything weird. They just shoot off to infinity. But we're so familiar with that all of these words can get kind of I don't know, stuffy. So, but that's all it's saying. They shoot off to infinity. Okay. So there's an intuition with pictures, and also, we could have imagine what this would look like. I'm going to write this first. Let's do another function. Gosh, what might that look like? Well, here's C. We're going to use the same C, and this is what it looks like. Here is a picture of a function, an example of a function that has this limit. It goes off to negative infinity. Okay. So how are we going to find some limits at infinity? How are we going to know, especially when we're given a function, an equation of a function, that we know where the limits at infinity are? We can say, yeah, the limit right here, if they ask us to find it, the limit is infinity. We'll look at that in just a second as I just take a brief moment to mention this other kind of limit where I could go like this. This is like negative 1 over x or something. And the limit doesn't exist. I mean, it doesn't even equal infinity or negative infinity because they go in different directions. But the limit as x approaches c from the left of, let's call it h of x, that's positive infinity. And the limit as x approaches c from the right of h of x is cramping me. I don't have any room. Negative infinity. Okay? So, there you go. That is, just really quickly, we can also have limits from the left and the right that go to infinity and negative infinity. So let's keep these actually and talk about how we're going to figure out where these limits happen. If they ask us to find the limit, we're going to be able to say, oh, it's infinity or negative infinity. Well, where is this happening? What is this feature called that exists? You can imagine it exists wherever a limit at infinity is going to exist for most functions. Well, a limit that is not a left or a right-handed limit it's gonna happen at a vertical asymptote. So now it remains to find a vertical asymptote, right? So we have to recall, how do we find a vertical asymptote? So let's use an example of, let's see, this function. And it's just going to be an equation. We're not going to draw any pictures, any graphs, anything like that. Alright, so we're not finding any limits or anything like that, but we are going to find a vertical asymptote because we know that if we have a limit of infinity, then we have a vertical asymptote at that value. Okay? So remember that order. If there is a limit of infinity, then there must have been a vertical asymptote. Now, there being a vertical asymptote doesn't necessarily mean that there's a limit of infinity, because here's an example of the contrary. So where do vertical asymptotes happen? They're clearly this really crazy thing that's happening. It's causing the function to kind of blow up at this point. It's some kind of math no-no is happening. Just like with a hole, or if you're putting a negative into a square root or something bad is happening. And with vertical asymptotes, they're coming from rational functions, and that happens where the rational function has a denominator of 0, because that's the only math no-no that would happen with a rational function. So wherever the denominator is equal to 0, that's where possibly, not always, but possibly you have a vertical asymptote, and we'll talk about the conditions in a bit. So I'm going to solve for x, and of course, if x equals negative 1, the denominator equals 0, and for this function, in this case, yes, there's a vertical asymptote. So at that vertical asymptote, perhaps, we have this limited infinity. Let's see another one. Yeah. How about a different function, g of x equals... and these, let me just slide these down, because we don't really need these anymore, and I don't want you to confuse yourself. These don't have anything to do with the pictures I had drawn. Equals x squared plus 1 over x squared minus 1. So wherever the denominator is equal to 0, we have a no-no, we have a problem. So let's factor And so x, whenever x is equal to -1, whenever x is equal to +1, we've got this function blowing up, so possibly we have some vertical asymptotes here at these points. It turns out they're vertical asymptotes. And let's look at another one. H of x equals the cotangent of x. Wherever this function has a problem, we may have a vertical asymptote. And we should recognize this is a technically a rational function is a ratio of two polynomials, but this is a kind of a rational function. The cotangent is the 1 over the tangent. I should write tangent. So wherever the denominator is equal to 0, we have a problem. So wherever the tangent of x is equal to 0, we have a problem. Where's the tangent ever equal to 0? Let's see. Yeah, the tangent's equal to 0. Well, okay. The tangent is the sine of x. Feel free to fast forward through what I just did, but it's too late for you now. Tangent is sine over cosine. And so wherever the tangent is equal to 0, we have a problem. So wherever the sine of x over the cosine of x is equal to 0, we have a problem. So wherever the sine of x is equal to 0, we have a problem. There we go. And that happens at 0 radians and pi radians and 2 pi radians and 3 pi radians, right? We could generalize this and say it happens at every multiple of pi radians, right? At n pi, this thing happens, and so that's where we have vertical asymptotes. Okay, so we're reminding ourselves, we're going to find the denominator of this function that we're dealing with, set it equal to 0, find out where that happens, and now we found our problems and we found our possible culprits of vertical asymptotes. Okay, but what about when they try to trick us, right? That third objective was that we not get tricked. I don't want that happening to us. And over x squared minus 4. Alright, so let's go at it the same way that we've been doing and say wherever the denominator is equal to 0. And so we solve this. X squared equals 4, positive 4x equals plus or minus 2. So at plus 2 and minus 2, the denominator is equal to 0. So we do have an issue. That's true. But you may recall that doesn't also always mean that we have a vertical asymptote. What we have to check is to see if we have another feature, which is called a hole. And I won't get into the details exactly right now, but if you were to about holes and all that kind of stuff. But remember briefly, if we were to graph this, remember we set it plus and minus 2, we should we might be thinking we have vertical asymptotes. But over here at positive 2, there is not an asymptote, but just this gap, this hole. That's what happens there. So how do we know where there is a vertical asymptote and where there's a hole? Which one is which? Well, remember from our experience in previous sections about finding functions that agree at all but one point. Finding this function that agreed at all but one point was a matter of finding common factors, canceling them out, and then we eliminate this hole. So this hole is happening between, it's a relationship between two factors of this function that are canceling out. So let's factor this guy, x plus 2, x minus 2. Alright, and now this guy up here, apparently there's some common factors, and we're getting a hole rather than a vertical asymptote. So ignore this, just giving myself more room to work up here. This is going to be x and an x. I'm thinking it's a minus 2 and a plus 4, and yeah, that works out. So look, this x minus 2 is canceling this x minus 2. Okay? I'm going to put quotes around it. It's quote-unquote canceling it because it is still there. You have to leave it there. You can't just get rid of it. Remember, that's not okay because the function is what it is. But we used it for finding limits and such. But we know that since we're looking for limits at infinity, a limit at infinity is not going to happen at 2, right? Because this is the factor x minus 2 that they have in common. And that kind of eliminates the possibility of a vertical asymptote at positive 2. Because this was the factor when you set it equal to 0 that gave you the positive 2. So rather than a vertical asymptote, we have a hole. So that's the part where we don't want to get tricked. So there you go. Now we know, what do we know? I'll sum up what we know so far. We know pretty much what an infinite limit is. You could like fill in that blank. We can find vertical asymptotes, and we can avoid getting tricked by holes that might be out there pretending that they're vertical asymptotes, but they're really just holes. But we haven't found any limits at all. We haven't determined if there's a limit at infinity or at negative infinity or anything like that. So here's where I'm going to use the example from the book, and then I'm going to depart from the book a little bit because the book is a little too calculator happy. Yeah, that doesn't make any sense, does it? Let's erase that. X is approaching 1 from the left for x squared minus 3x over x minus 1. Okay. So, what's the limit as x approaches 1 from the left of this function? So, maybe it's infinity, maybe it's a hole. Let's find out. First, let's factor out. And we're going to, this process is going to get a little bit faster, a little bit smoother as we understand what's going on. We can look right here and we know that 1, if I put in a positive 1, obviously this is a problem value. So am I approaching a number? Am I approaching infinity? What's going on here? I'm going to factor out a common factor of x. This is going to be x minus 3. Okay. Now, is it a hole? Do we have a situation from before, like where we found a simpler function and canceled that out and found, you plugged it in and everything was wonderful? No, it's not a hole. Okay, so we do have a vertical asymptote. So it just remains, what are we doing here? What are we approaching? So let's see. Let's just admit that if we use our calculators and we plug this in and we found this picture that goes like this, we can easily say, well, as it approaches 1 from the left, it's going to positive infinity. That's way too easy. So why don't we know this guy is going to be acting, it's going to be trending, it's going to have a trend in a certain direction. So let's do something kind of, more like math, where we say, let's plug in a 0. Let's plug in 2 values and get close to 1 from the left, right? F of 0, and then let's find maybe let's start with f of negative 1 and then go to f of 0. What are we doing? We're coming in from the left with these values. And what are we looking for? Well, if the values, the y values, the outputs are getting bigger, it must be going up. And if they're getting smaller, they must be going down. So let's find out which it is. F of negative 1, that's going to be negative 1 times negative 1. I'm using the factored form up there. Over negative 1 minus 1. So this is going to be negative 1 minus 3, that's negative 4, and then that'll be positive 4 up there. And over negative 2, that's negative 2. And now, f of 0, well, we've got 0 minus 0, that's 0, so it's going to be 0. And we see that our y values are going from negative 2 to 0. They're getting bigger, they're going up, they're going towards positive infinity, so this must be positive infinity. If you want to wimp out and use your graphing calculator, I can't stop you. But here's, there's a more pure and dignified way to do this. Alright. And, then we can look at the properties of infinite limits, but it pretty much says something that you would conclude by your intuition. If you have some function whose limit as x approaches c of f of x is equal to infinity, and you had some other function as x approaches the same value of g of x, and it's equal to just some number, right? There's no going off to infinity, it's just some number. Then if you were to ask, what's the limit as x approaches c of f of x plus or minus g of x? Well, the limit of f is really, really big. It's positive infinity. The limit as just a moment. And the limit as x approaches c of g is just some number. So adding or subtracting some number, no matter how big it is, versus infinity, the hugest number, it doesn't stand a chance. So whether you add it, you subtract it, eventually it's still going to go to infinity. There's nothing you can do about it. It's inevitable. Okay, the limit as x approaches c of f of x times g of x. Right? Well, this guy's really big. And then what happens if you multiply it by a number? I guess it depends, doesn't it? If g of x were positive, it would just make the big thing even bigger. So it would make it positive. So this is if L is positive, and the limit as x approaches c of f of x times g of x equals negative infinity if L were less than 0, right? If it were negative, then of course it would make this infinity a negative infinity. So just kind of flip the whole thing over and kind of make the magnitude bigger in the negative direction and so on, unless it was a decimal. Quotient the limit as x approaches c, the only quotient we talk about in the book apparently is g of x over f of x. Well, g of x is a number, f of x is a huge infinity, and a number divided by a giant number is 0. So there you go. If you were to flip it over, if we investigated that, you'd find out, well, it'd still be infinity or negative infinity depending on what g of x was. And then, what if f of x were negative infinity? Well, then not a whole lot would change. This would become negative. These would switch. This would be negative. This would be positive. This would still be 0. Negative 0. That doesn't mean anything. Okay, so I hope we have a good intuitive grasp of all these things, and we'll do some sample problems here in the next video.